All right, so last lab that you guys will be doing is on electromagnetic induction. This one is very conceptual. So the very first thing that you'll do, there are 3 questions. There's a blank page here because it's how Google Drive took it. So you've got Faraday's law, just describing what it is. If you don't remember, it's in the introduction. Faraday's law tells us that whenever there is a change in magnetic flux through some coil of wire, then we get a voltage or an EMF out as a result. So we talked about this from the standpoint of microphones, where we had either a moving magnet or a moving coil microphone, where a thin diaphragm was moving, typically with the coil, but it could have a magnet attached to it, was moving a coil closer or further away from a magnet, or the magnet closer or further away from a coil, which gave us a small voltage, which we can then amplify and record, or amplify through a sound mixer and play that. So Faraday's law, in words, a changing magnetic flux creates a voltage, or EMF. Electromotive force and voltage are essentially the same thing. They're technically slightly different, but the difference is so minimal it's not worth worrying about. Now, the other thing is, if you remember Faraday's law, there is a negative sign on it. It's the EMF equals minus N, which is the number of turns in the coil, times the change in flux with respect to time. Actually, let me look up here. It might be up. Okay, so yeah, this is for one coil. We have EMF is equal to the change in flux over the change in time. The minus sign is what expresses Lenz's law, because Faraday's law, whenever there's a change in the flux, the system wants to oppose that change in flux. So if your flux is increasing, the EMF is opposite to that change in flux to try to cancel it out. And that's where Lenz's law comes in. Lenz's law is dealing with the direction of the voltage, and Faraday's law is really more concerned with the numerical amount of the voltage that's created. So, kind of in words, Lenz's law is the induced current flows. The current induced by a changing flux flows such that the magnetic field opposes that change in flux. It's really weird to kind of describe. It's something that in a physics class you do several different examples to kind of understand it, but ultimately that means if I have a coil of wire and I'm bringing the north pole of the magnet toward that coil of wire, when there's a voltage created that makes a current flow in that wire, it's going to make the north pole of that coil with the current flowing point towards the north pole of the magnet, so that it's trying to stop that magnet from coming in, and 2 north poles will repel one another. But it's ultimately not really strong enough, because the effect is scale-wise so much smaller than what's typically causing the EMF that it can't overwhelm it. And then the third question is kind of just going over what I just described, answering that question: what happens to the current in a coil of wire when a north pole of a magnet moves toward it? So the actual simulation is very qualitative. We're not worrying so much about numbers today so much as behaviors. This is a Java lab, so I'm going to go through this speaking, showing you what the questions are actually referring to, and I'll also post a video with me not really narrating, just following along with the instructions for the people that can't access it. So I'm going to go ahead and hit this, download it, open it, because I do have Java on this computer. So what you'll see when you open bar magnet and compass. And so the first thing we're just talking about is the magnetic field around that bar magnet. So the red end of the compass needle is attracted to the north magnetic pole. Sorry. Brain just locked up for a second. Okay, so we've got this here. A compass is actually a little mini magnet. The red end is the north end of this magnet. The white end is the south end. You'll notice that as I move this around, the red end always points toward the south pole of the bar magnet. Doesn't matter where I set the compass, it always points, well, when I'm close to it, points toward the south pole. When I get close to the north pole, the white end points toward the north pole. And that's what we expect. If you have two bar magnets, the north repels the north, the south repels the south, but the north attracts the south. Well, the compass needle is actually a mini bar magnet with the red end being the north end and the white end being the south end. Also around this, you can see all of these other little mini compass needles. This is showing you the direction of the magnetic field, and the brighter it is, the stronger the field is in that location. So first question, if the red end is attracted to the north, which pole of the bar magnet does the north pole of the needle point to? So what they're asking you is, sorry, forgot it's not in browser, is which end of the magnet does the red end of the needle point to, or compass needle point to, which is pretty obvious. What happens when you move it to the other side? So if I move this around over here, you'll see that I'm attracting the white end, which is the south end of the compass needle. Let me just close this so I'm less tempted to open it back up. So then we go to the Electromagnet tab. Let's scroll this down a little bit. And when we open this up, we've got a battery. It's running a current through here, which we can see. The battery voltage is set to 10 volts. So the first question, which side of the coil does the north magnetic pole point to? So I just want to bring this down here. And which side does the red end point toward? Well, it points toward the left end. If I move this over here, you'll see that that points toward this end. So as I move this around, it's very similar to a bar magnet. In fact, it's identical in shape. The bar magnet is just longer, so it's more spread out, as opposed to this where the change in that magnetic field happens pretty quickly just because that's a small coil of wire. So given what you see there, which side of the coil is its north pole and which side is its south pole? This is using what you learned about the bar magnet to assign the north and south magnetic pole to the electromagnet as it's set up when you just come into the sim. So the next thing is we're going to reverse the voltage, basically. We're going to take it from 10 volts to 10 volts in the other direction. And you'll notice now that the sides that the compass points to have flipped around because the current is going in the opposite direction. Here, the current flowing is going to give me, if I flip this back to the way it was, you can see with the electrons coming in here, circling around and coming out there, I end up with my north on this side. Now, if the electrons go in here and circle around and come out there, now my north is on this side. So when you're dealing with an electromagnet like this, the direction of the current is going to change depending on, the direction of the magnetic field is going to change depending on the direction of the current. So when I flip my battery voltage around, I also flip my magnetic field around. So you'll first describe what happened to the field, which side has its north and south magnetic poles, and then describe how the orientation of the field depends on the current. All right, so now we'll actually get to the induction part. So we are going to go to pickup coil. And our pickup coil, we have 2 coils of wire here, a bar magnet, and a light bulb attached to it. So what we want to do is move that bar magnet around and see what happens. So you'll see as I move this around, I get a little bit of response on the light bulb, but over here it's not tremendous because the magnetic field is relatively weak. But if I bring it through the coil of wire, you'll notice that I get a big response momentarily as I move this through. If I move it through really slowly, though, I can keep this almost to a minimum. But if I go through really quickly, you'll see, hopefully, I don't know how the Zoom recording is going to show up with this, you'll see that momentarily I get a really bright flash because I move this through really quickly. If I move it through really slowly, I never really get a big response. I just get a little bit of light. So the speed at which I move this through matters because the faster I move it through, the more quickly I'm changing that magnetic flux and the bigger the voltage that the light bulb gets as a result. When I move it through really slowly, well, now I'm making the change in flux really slow, which makes the voltage really small and the current really small as a result. So the first question is just what happens when you move the magnet through the coil, and then does the response depend on how fast you move it, which I think I just showed you. So the next thing is we're going to change our indicator from a light bulb, which is insensitive to the direction I'm going. I get a light no matter whether my current is flowing one direction or the other. So I'm going to switch to this galvanometer thing, which will indicate when I get a positive voltage and a negative voltage. So you'll see here as I move this through, as I move the north toward it, it deflects in the negative direction. Now if I come around here and I move the south toward it, I still get a negative direction because I'm coming in from this side. But now let me bring my magnet back over here and hit this flip polarity button. So now I've got the south moving toward this. Notice that when I move the south toward it, it's a positive deflection. So the first thing is what happens to the galvanometer needle when I move it? Well, it's going to move either positive or negative depending on whether I'm moving the north or south toward the actual indicator or toward the pickup coil, or the direction I'm moving it. So when I moved it, you might not have noticed, but let me flip this back to the north. So when I move it toward, I get that minus deflection, but when I move it away, I actually get a positive deflection. So what's going on is when I move it toward, I'm getting a voltage in a certain direction to try to oppose that increase in the magnetic field through the coil this direction. But when I move it away, now I'm decreasing the magnetic field strength still in this direction, and the voltage has to flip to try to keep the magnetic field as strong as it was before. So when I'm making it stronger, it wants to weaken the field from the magnet. But when I move it away, when I make it weaker, it wants to strengthen the field from the magnet. And this is where Lenz's law comes in, because when I'm moving toward, I'm increasing the flux. When I'm moving away, I'm decreasing the flux. So Lenz's law says when you increase the flux, you want your induced field to point in the opposite direction. When you decrease the flux, you want your induced field to point in the same direction. So you get asked about what happens and then whether the direction of motion influences it. So that's just saying, when I move the north toward or away, does that change my deflection? The next questions are dealing with the controls at the bottom. Scroll all the way down. All right, so we're going to increase the number of loops first. Okay, so first thing, I'm gonna go ahead and just define that as my speed. I'm gonna try to move it at the same speed, but it's hard to do. Okay, now I'm going to increase my number of loops, which I can only go to 3, but I increase from 2 to 3. And you might have noticed that it's a bigger deflection. An easier way to see this would be to take it down to 1 and measure that deflection, and then to increase to 3, and you can easily see that that deflection is bigger. So when we increase the number of loops, we get a increase in the deflection. The needle moves further. And that comes from Faraday's law, where we have the number of loops directly in Faraday's law. Because what's going to happen in this is each of these individual coils is going to generate the same voltage. So let's just say, for sake of argument, one coil is generating 1 volt. So if I have 1 coil, I get 1 volt. If I have 2 coils, I get 2 volts. If I get 3 coils, I get 3 volts. So as I increase the number of turns, I just get a larger voltage naturally. And this is how you actually get more signal in a pickup, in an electromagnetic pickup. If there are more turns, then you get a bigger signal, which is why if you ever look at an electric guitar pickup, pretty typically it uses really, really thin wire. And that's so you can have lots and lots and lots of coils in the pickup so that the signals that are coming out of it are big enough for an amp to work with. So the next one is what happens when you change the area. So down here as well, we had loops right there. Now we're going to go area. I'm going to take this all the way up to 100%. I'm going to go ahead and leave it at 3. Actually, let me put this back down to 50 real quick, just so we have our reference point. So as I move this through, I get maybe to this first notch here, big notch. Well, I'm going to try to move it through. Now I'm going to go ahead and increase the area and do the same thing. And I maybe got past the second notch there. So what's going on with this is I see a bigger deflection here because I increased the flux since the area is directly measured in the flux. So I have the same bar magnet, but magnetic field times area is the flux. So at 50%, my area is smaller, so my magnetic field times the area is going to give me something that's 1/2 of B times A if this is A as a whole. So here I would have B times A, which, well, it's actually a little bit less than B times A, but roughly double what I saw with the 50% mark. So it's not exactly double because I can't move this at exactly the same speed, but you'll just have to do your best with it. All right, the last two questions deal with the transformer tab. So I'm going to come here. First thing, blah, blah, blah. Move the electromagnet and observe what happens to the coil. So in this case, we are just taking this and moving it around. We can't, oh, I guess we can run it through. You just want to compare the behavior here to the behavior for your pickup coil with the bar magnet. So we're going to compare this to this. And the behavior is very similar. In fact, for the light bulb, it all works out the same. You could switch to the galvanometer meter and notice that when I have my current flowing this way with the north being on this side, it behaves exactly the same as the bar magnet. So this is just asking how does the response to the electromagnet compare? And then given that, what does this mean about the magnetic field created by the electromagnet as compared to a permanent bar magnet? And that's it. So this one is very conceptual. There's no numbers involved really at all. You can, on the part where you're using the indicator, say, well, I got to the second notch, but it's not really necessary. This one I will probably just check to make sure you finished it more than anything. And so I'm not going to grade this one that hard at all because there's not really a lot to it. And that's really all I have to say about it. So I'll put this up on a video page tomorrow, which will be Monday morning, with the unnarrated version where I'm just following through. So I'll kind of switch back and forth and I'll be like, I'm doing this now without actually saying that. And you probably can answer it from this video as I've gone through it, but just in case, I'll do that as well because I know not everyone can get Java running. So that's about it. And again, this is the last lab. Realistically, as long as everything past lab 6 is in by the end of the semester, then I'm going to grade it. And I probably won't take anything off just because at this point, we're back a week and it just doesn't really behoove me because I don't know what's going on in everyone's lives to sit here and be like, well, you're a week late. This is 10 points off. Especially on the earlier labs where there were issues with the simulations. So, yeah, this one's officially due the Tuesday after next, which is would have been our last week of classes. And when it comes to grading submissions, I'm probably going to get caught up on a lot of that over the next couple of days. I was a little under the weather with stomach stuff this week, so there were a couple of days where I didn't really do much. And so I'm kind of getting myself caught back up. And I'll get caught up on your grades, probably get at least through lab 10 graded here pretty soon for you guys. Like I said, I imagine no later than Tuesday. I might just get them all done tomorrow. And as well as any late submissions on 7 and 8. So that way you'll know where your grades are. And that's really about it. So good luck on this, and I will be recording the other videos shortly to put up, and you can see those soon. So good luck.